Good day. My name is Caroline Apovian. I am the director of the Nutrition and Weight Management Center at Boston Medical Center, and I'm a professor of medicine at Boston University School of Medicine. And today we're going to talk about obesity, why we're unable to lose weight and keep it off in this environment, and all of the research over the past 20 years that have helped us realize that obesity is a disease. And it's a disease chiefly because of the connections between the gut and the brain. Before I move ahead, I want to remind you that if you have any questions throughout the broadcast, please do submit them, and I will answer them after the webinar is over in the last few minutes. So, as I just said, obesity is now known to be a chronic disease. It has a very complicated etiology, and this slide really depicts probably just a partial listing of the interrelated factors that cause obesity. So, we first want to talk about genetics. It is certainly the case that what genes you end up with have a lot to do with your predisposition to developing obesity in the right environment. Not only do your genetics have a lot to do with it, but the interaction between your genes and the environment, which we call epigenetics. And there are single gene mutations that certainly cause obesity. They're rare, however. One of these mutations is the mutation in the leptin gene, such that there are a few families around the world that have this leptin single gene mutation, and giving back leptin, which I'll talk about shortly, does get these people to lose weight. But in the general sort of garden variety obesity, you have many genes that are in play and not a single gene mutation. We also have a lot of environmental and behavioral factors that have caused an increase in the predisposition to gain weight. Certainly our diet. So our diet, especially in the United States, but elsewhere also, is very high in fat and calories. There's a lot of fast food available, so we don't have to expend too much energy to get 3,000 calories in a meal, for example. We can just roll down, well, not even roll down our window anymore at the fast food place, but push a button and get 3,000 calories in 2 minutes. Inactivity, we don't do as much physical activity as we used to because of technology. Emotional factors, depression and anxiety can lead to overeating. Lack of sleep. A lot of studies have shown that short sleep, 6 hours or less a night, alter gut hormones so that you end up eating more, which we'll talk about. Smoking cessation. People who smoke or used to smoke enjoyed a higher metabolic rate. However, when you stop smoking, you don't have that higher metabolic rate, and you start to, if you eat the same way you did or even overeat because you're not smoking, you can gain weight. The environmental factors, socioeconomic status certainly has a lot to do with obesity. The lower the socioeconomic status, the more the predisposition to being overweight, chiefly because of the foods that you have available. Access and affordability of food, for example, but also the built physical environment. So if you live in a very urban area as opposed to rural, you may not have access to parks and sidewalks. Stress, different cultures, sociocultural attitudes revolving around food have a lot to do with our interaction with the built environment and the current availability of food. And there's this thing called endocrine disruptors. These are non-food items that are in the foods that we eat, chiefly preservatives and fertilizers and things to make food last longer that can, at least in the petri dish, have been shown to predispose one to metabolize fat differently and maybe store fat instead of burn it, for example. And then the gut microbiota, we have many, there's a lot of research suggesting that the types of bacteria in our gut have a lot to do with what we absorb and what we don't absorb. There's not enough time to talk about all these factors. There are medical conditions leading to obesity, such as polycystic ovarian syndrome, Cushing's syndrome, hypothyroidism. Medications, there are many medications that predispose to weight gain. Antipsychotics, insulin, sulfonylureas, steroids are just some of the examples of medications that can predispose to weight gain, and you need to know about them in order to help your patient. Post-pregnancy weight retention is certainly very common as well. And aging. The aging leads to muscle loss, and the muscle loss, of course, leads to less physical activity and predisposition to store fat. And then we're going to talk a lot about altered homeostatic and reward system pathways. So the brain has an area in the hypothalamus which is called, it controls appetite and satiety, and pathways leading from the gut, fat tissue, and the pancreas can either activate or deactivate that system, leading to appetite or satiety, increased appetite or increased satiety. And we have some evidence that some alterations and disruptions in these pathways can lead to obesity. And then these disruptions can also alter the level of hormones and GI peptides that this area sees. And then we also see that we can create a new body set point in people with obesity by surgery, by the gastric bypass, which alters levels of hormones and GI peptides seen by the gut and by the brain, and we'll talk about those. So obesity is a disease. We have now, ACE has created a complication-centric model for the care of the overweight obese patient to take into account treatment of this disease. So this is on the web. This has been published in Endocrine Practice, and you can look this up and see that the first step would be an evaluation of what kind of other diseases does that patient have. Are they metabolically healthy or metabolically unhealthy? If they're unhealthy, do they have cardiometabolic disease or biomechanical complications of obesity, such as osteoarthritis, for example, would be considered a biomechanical complication. Whether or not they have either of these, you still need to treat, and step 2 would be selection of the treatment modality after you assess for complications. And notice that that there is lifestyle modification. There is also MD, RD counseling, medical therapy, and the types of therapies on the right. And then there's also surgical therapy if it's indicated, if the patient's BMI is over 35 with a comorbidity. We will talk about these therapies. So let's first talk about the physiology of energy expenditure. Energy homeostasis is something that the body tries desperately to find. So body weight is tightly regulated, and the body likes to be at a certain body weight. That's why you get hungry when your body needs calories, and you get full when your body is satiated. And the whole thing revolves around keeping your body at a certain body weight. If you increase, on the right here, if you increase energy intake by ingestion of proteins, fat, and carbohydrates, you will increase your body weight. If you decrease it, you will decrease your body weight because your energy expenditure, if you increase your calories, you'll gain weight. If you'll decrease your calories, you lose weight. And the body, if you increase your calories, the body will respond by trying to increase your energy expenditure so that you maintain a body set point. Certainly, if you keep increasing your energy intake, the body will lose and you will gain weight. But there is a certain physiology that is in play to keep your body weight where it is. We'll talk about that further. Brown fat has been discovered recently to be present in adults and not just babies, and in animals. We know that there's a lot of brown fat in animals. It has a lot to do with thermogenesis. Brown fat is distinct from white tissue, white fat, because it produces heat, which in animals protects mammals from hypothermia. And the way it does that is to have a proton transporter which uncouples mitochondrial respiration, releasing energy as heat. So it's kind of good to have if you are interested in burning calories, because it uncouples respiration and creates a futile cycle where the energy that you take in is released as heat. So heat production certainly occurs in response to cold environments in adult humans and in babies, and in eating high-fat food. So when you eat high-fat food, and which has a lot of calories, you start to activate brown fat and burn off those calories. But if you continue to do that, you will gain weight. And it has been thought that defective UCP action could be linked to the development of obesity. So here is brown and white fat, how they're different. They are different because this is brown fat. You can see it's full of mitochondria compared to white fat, which stores fat in the middle here. And so the nuclei are pushed out to the side. Brown fat is smaller than white fat, and the energy that is released as heat, whereas in white fat you store the fat. Brown fat prevalence, so how much brown fat you have, has to do with your age and your body mass index, as is shown here. The older you are, the less brown fat you have, and the bigger you are, the higher your BMI, the less brown fat you have as well. Generating the question, is it the lack of brown fat that causes obesity, or maybe a dysfunction of brown fat? What's causing the obesity here? Which came first, the chicken or the egg? This is how you can visualize brown fat by PET-CT, and that's how we discovered, actually, researchers discovered that there is brown fat in humans. So the brown fat really is prevalent in the subclavicular area here. This is all brown fat, and you can actually measure brown fat this way, but it's pretty expensive to do so. So it's just used in research right now. Now, depending on your brown fat activity level, so this is a study in overfeeding. When you overfeed someone, your 24-hour energy expenditure increases, and obviously so does your mass, your weight. And depending on the person and how much brown fat you have, the increase in energy and the increase in your weight can be a certain percentage of fat-free mass and a certain percentage of fat mass. So it depends on the person. So these are 5 different subjects, and you can see they all gain weight because they're being overfed. But it depends on the subject what is fat and what is lean mass. So let's integrate this a little bit. Let's go and now talk about the hypothalamus and the integration of peripheral and central signals. So as I said before, the CNS has systems that called the homeostatic system and the reward system that takes in signals from the periphery. So what are these peripheral signals? These signals, one is insulin, one is leptin, we also have ghrelin and PYY. Insulin comes from the pancreas, as you know. Insulin is secreted from the pancreas to take care of your blood sugar. And insulin also enters the brain and enters the homeostatic system, which is in the hypothalamus, and causes satiety. Leptin does the same thing, but leptin is a more long-term signal coming from fat tissue. Leptin is secreted from fat tissue at a homeostatic level, and changes in leptin occur when you, for example, you lose fat because you're on a diet. When you lose fat, you're on a diet, less leptin goes to the brain because less leptin is secreted from fat tissue, and eventually you get hungry because less leptin is causing satiety until you regain that fat mass. That's why it's a homeostatic signal. Ghrelin is a more short-term signal from the stomach right before you eat and it's the only hunger hormone that we know. The others cause satiety. Ghrelin causes hunger. PYY is secreted from the small intestine when you generated enough food ingestion through the intestine, and those cells secrete PYY, which go to the brain and cause satiety. Those are some of the examples of peripheral signals. So these systems regulate appetite, energy expenditure, and also reward. So there's a reward system which can override the homeostatic pathway that I just talked about. So and this happens in periods of energy abundance because, you know, after all, usually when you eat dinner, you're full. Homeostatic system causes satiety. But when the chocolate cake comes out or the ice cream, you've still got the desire to eat that ice cream, and that's the reward system working. So you have these two pathways. The reward system can override the homeostatic system. Okay, and the reward system feeds from other parts of the brain to get you to keep eating even though you're full. Homeostatically, you're full. So there's the hypothalamus, the regulation center of appetite and energy, and the peripheral signals to the hypothalamus come from areas of the body, including fat tissue that's secreting leptin. You've got the intestine, so stomach secretes ghrelin. Insulin comes from the pancreas. You've got the small intestine secreting PYY here, and GLP-1 and oxanthomodulin, two others that cause satiety as well. They all get integrated in the hypothalamus to regulate your body weight. Notice that we only know one appetite-stimulating hormone, which is ghrelin. And the brain systems receive those signals, and the peripheral systems send them. All right, I just want to make one other point. The vagus nerve here is also receiving its these signals go into the bloodstream, but some are also directly go to the brain via the vagus nerve also. So we have redundant systems here, and the vagus is also a system that can be regulated. So you've got your energy balance. If you restrict by caloric restriction, fasting, or exercise, you get negative energy balance. If you overfeed, high-fat diet, and you're sedentary, you get positive energy balance, and you end up gaining weight. So again, just an overview of all the gut hormones we just talked about: PYY, pancreatic polypeptide, GLP-1, oxanthomodulin. These suppress appetite, and they come from the gut. The only one that increases appetite is ghrelin, and these are modulated by acute food ingestion. However, you've got short and long-term energy homeostasis through leptin, which comes from fat tissue, and insulin that comes from the pancreas. Another summary. Notice that all of these hormones have other actions besides appetite and satiety regulation. So, for example, PYY delays gastric emptying, GLP-1 decreases blood glucose. So you've got dual actions for some of these gut hormones. Now, the interesting part is that why are we developing obesity? Why do some of us develop obesity at a young age, others at an older age? So, obesity, it looks as if it's associated with hypothalamic injury, at least in rodents, and some suggestion that this is true in humans. So there are rodent models of obesity that consume a high-fat diet. And researchers have found that not only do you get inflammation in the fat and peripheral fat tissues, but in the hypothalamic areas that are critical for energy homeostasis. Hypothalamic inflammatory signaling was evident in rats and mice within 1 to 3 days of high-fat diet onset, prior to gaining a lot of weight in these animals. So this was kind of a breakthrough that maybe it's a disruption of the appetite and satiety pathways that are doing this. So what they found in pathology is that you saw reactive gliosis and markers suggesting neuronal injury in this hypothalamic area of appetite and satiety in rats and mice within the first week of high-fat feeding. And then these researchers then thought to look at MRIs of obese humans and found evidence of increased gliosis in the hypothalamus of obese humans. What does this mean? The suggestion that obesity is associated with neuronal injury in the brain, crucial in the area crucial for body weight control in animals and rodents. So, meaning, what does this mean? It means that perhaps if you eat a high-fat diet or a lot of calories, especially when you're young, and you continue to do so, if this is true, that it happens in humans, you get this hypothalamic inflammation, which causes a disruption of the appetite satiety signals, and you no longer are aware that you're full because the signals aren't getting to the brain, and you keep eating. That needs to be really confirmed in humans. The suggestion is there, but it's certainly true in animals. Very interesting. So why can't people lose weight? Really, it's why can't people keep the weight off? I just told you that the research is out there suggesting why, but let's look at the studies. So this study was published a few years ago, looking at 3 different diets: low fat, Mediterranean, low carb. Dieters lost weight within the first 6 months or so, and then when the dieting stopped and patients were allowed to eat whatever they wanted, they did regain weight. And it didn't matter the type of macronutrients in the diet didn't matter. Everyone gained weight, everyone lost weight. So this is called the fat trap, why people regain weight. Basically, you've got genetic developmental factors. However, there's inflammation and neuronal injury in addition to the increase in calories from the diet that create the situation where you keep eating and the satiation signals aren't getting to the brain. So again, you're eating a high-fat, high-carb food diet, the typical types of food that are very prevalent in this society, and certainly in low socioeconomic backgrounds. You get CNS insulin and leptin resistance because of this disruption of neuronal pathways, and insulin and leptin are not producing satiety. The brain cannot tell how much fat is stored. You get this reduced sense of satiety and craving, increased weight gain, and you get this feed forward. It's a feed forward phenomenon. So a feed forward phenomenon. Keep eating. That's what happens. So the fat trap. Another study showed in these dieters getting in very low calories, 500 to 550 calories a day. At 10 weeks, there was a 30-pound average weight loss at year one. At year one after the dieting, which was 10 weeks long, patients gain on average about 11 pounds. And the point here is that patients reported feeling hungry, more hungry and preoccupied with food than before the weight loss. Here is what this looks like. So you have patients losing weight, 10 weeks, and then regaining weight, 11-pound weight gain. And they measured the hormones I was just talking about and found leptin reduction at the end of a year, PYY reduction, CCK reduction, insulin reduction, and amylin reductions. All of the satiety producing hormones were reduced, and guess what? Ghrelin, the only hunger hormone that we know, was increased. And also measures of appetite showed a lot of increase in appetite. 14% weight loss produced changes in 8 hormones that encourage weight regain. So, and this is what it looks like. Ghrelin levels were increased, PYY decreased, CCK decreased, and amylin decreased. Hunger increased, and the desire to eat increased as well. And so these changes in hunger and the desire to eat produce that weight regain. In addition to this, so this is all evidence that it's very difficult for us to keep the weight off when we lose weight because of these gut hormones. Studies were done looking at resting energy expenditure, and resting energy expenditure, a decrease in resting energy expenditure is found to be a determinant of weight regain in a series of long-term dietary interventions. So 90 publications showed that you get a decrease in your resting energy expenditure when you lose weight. And what kind of a decrease in energy expenditure? Well, after a review of lots of publications, roughly 15 calories per kilogram of body weight loss. So every time you lose a kilogram, your resting energy rate decreases by 15 calories. So, in other words, if you lose 10 kilograms, you get to eat 150 calories less per day. Very difficult to do in this environment. So again, just to summarize all of these key hormones, either suppress appetite or increase appetite. Actually, the only one we know that increases is ghrelin, and these are key hormones that are associated with weight gain and regain after losing weight. I want to mention one more thing, which is another hormone that comes from muscle. Irisin was discovered a few years ago. It's secreted from muscle into the blood and activates, what does it activate? It activates white fat and turns it into brown fat. All right, so irisin acts on white adipose cells in culture, at least, and in vivo, to stimulate UCP1 expression and a program of brown fat-like development. So how do you increase irisin? You exercise. Irisin is induced with exercise in mice and humans, and increased irisin levels in blood cause an increase in energy expenditure in mice with no changes in movement or food intake, resulting in improvements in obesity. So the bottom line is irisin could be therapeutic for human metabolic disease and other disorders that are improved with exercise. So you want to increase irisin, exercise, and you may be able to keep the weight off. And this is like a breath of fresh air to me. It also a light bulb went off when I read about this, because now we know why exercise is so important in preventing weight regain in those who have lost weight, maybe due to irisin. So here's a schematic showing that irisin is produced during exercise. Irisin is produced causing a browning of white adipose tissue enriched with brown adipocytes that produce UCP1 and increase your resting metabolic rate. So these are all beg the question for how we can help people lose weight. If we have this hypothalamic inflammation, if we also have determinants of browning of white fat, which with irisin produced by exercise, what does that mean for new therapeutic options for helping people lose weight and most importantly, keeping the weight off? Well, we have anti-obesity medications. There are many that have been researched. A few are out there that have been FDA approved. When do we use them? We use them for patients who have tried diet and exercise for at least 6 months and behavioral change, because that's the core. You know, if you can change the way you're eating, eat more fruits and vegetables, more whole grains, and more protein, and stop eating fast food, maybe that will be all you need. But if it's not, pharmacotherapy can be used for patients with a BMI over 30 or over 27 with at least another disease like hypertension, dyslipidemia, heart disease, diabetes, or sleep apnea. That's how you use these drugs. What are approved? So we have a new agent approved since July 2012. It's called Qsymia, which is a combination of a little bit of phentermine and a little bit of topiramate. They both can help you lose weight, but the combination has shown less side effects than either alone, and that's why they've combined them to produce Qsymia. Phentermine is a noradrenaline and dopamine releasing agent. Topiramate is an anticonvulsant and has GABA modulator properties. Some of the side effects are listed here. Not too bad. Dry mouth, tingling, constipation, altered taste, upper respiratory infection. Well, I don't think so. But lorcaserin, another drug approved in June 2012. It's called Belviq, brand name. Selectively targets the 5-HT2C receptor, producing satiety. Both of these produce satiety in different parts of the hypothalamus. Side effects: headache, dizziness, nausea. Why do we say it selectively targets the 5-HT2C receptor? Because it's the A and B. It was the B receptor that caused valvulopathy with the old fen-phen, the fenfluramine, and Redux years ago. There are many in development. So if you remember me talking about GLP-1 and oxantimodulin, GLP-1 agents are already out there for diabetes. This one, liraglutide, is being looked at as an obesity agent, but we also have pancreatic polypeptide and amylin being looked at for, they're in phase 3 trials for obesity. Some leptin analogs and others that are not quite ready yet. So what are the mechanisms of action of some of the obesity agents? Well, phentermine, which has been around for a long time now, it is in the combination phen-top, which is Qsymia, increases norepinephrine levels in the hypothalamus and causes a sympathetic response that causes satiety. Sibutramine, which is an old drug, it's now it's been taken off the market for increase in stroke, but it was a reuptake transporter of 5-HT and norepinephrine, and it caused satiety in the hypothalamus. Rimonabant also was never approved, so I won't talk about it. The only one that works outside of the hypothalamus currently is orlistat, which is Ally or Xenical. Works in the gut to malabsorb about 30% of fat calories. Other molecular targets, we can talk about topiramate here, which works on GABA, and the combination of topiramate and phentermine produces good weight loss with less side effects than either alone. You have lorcaserin working over here. So here's the center of appetite and satiety right here, and here's where some of these agents work. There are two neuronal pathways here. One produces, when stimulated, causes an increase in appetite, the other an increase in satiety, and they all sit within the hypothalamus, and here's where some of these drugs work. So pramlintide, which is amylin, works peripherally here, and then works on some of these targets later on, where some, like lorcaserin, work directly in this hypothalamic area. Very, very complicated, as you can see. And some of these are already out, some of them are being looked at. The ones that have numbers, obviously, are in research. So what are other strategies to develop these anti-obesity drugs? So there are those that work in the hypothalamus, but in the future we need those that work through modulating exercise. So for example, maybe irisin analogs can do what exercise does to brown white fat tissue, for example. So you've got to somehow decrease sedentariness and increase exercise. We have caloric restriction that occurs with the appetite suppressants currently. And so the future will combine behavioral interventions with these drug therapies to push the envelope on weight loss and, more importantly, weight maintenance. So the future for the targeted drug interventions, again, here we have the appetite and satiety regulating center in the hypothalamus, the two sets of neurons. One increases food intake, the other decreases food intake, and we have the hormones that modulate this hypothalamic area. You've got the combination of topiramate and phentermine available. You've got lorcaserin available. Pretty soon we'll have a combination of bupropion and naltrexone available. Naltrexone is an anti-addiction agent. The combination of this and this causes a synergistic effect. The bupropion works, however the naltrexone blocks the negative feedback inhibition, and so it works better. What you want to do is get combinations of these drugs, and also maybe combinations of these gut hormones here, pramlintide, exenatide, liraglutide, which are GLP-1 agonists, combined with some of these others to work in several different areas. That is the future. Now, in the remaining few minutes, I'm going to talk about really the only cure we know for weight regain, which is bariatric surgery. And why is that? I will explain why. Here are some of the surgical procedures. We have the purely restrictive procedures, which are the lap band, which is an adjustable band that is placed around the stomach here, that hooks onto a port, which is subcutaneous. You inject saline into this port, and the balloon here expands and causes obstruction or narrowing of this pouch. which produces satiety. You also have the laparoscopic sleeve gastrectomy, which is now known as more of a malabsorptive procedure also, not just a restrictive, but you cut part of the stomach out. So here was that stomach, it's thrown out. And here is the sleeve of stomach that's left, and the food goes down this way. And as you can see, you have less space for food to enter, and that causes a restriction of calories. But also, you also have cut out some of the cells that produce ghrelin here. So you get satiety from altering gut hormones as well. That's why you get more weight loss with the sleeve gastrectomy than the lap band. You also have a new procedure called the gastric plication, where you involute the stomach, as you can see here. You involute the stomach, and you end up with a sleeve, just like here, without throwing out and cutting into the stomach. So these are the restrictive procedures. Here are the metabolic procedures. We call them now metabolic procedures and not malabsorptive procedures, because we're metabolically altering gut hormones. What do I mean by that? With the Roux-en-Y gastric bypass, we create a small pouch here, and we cut into this part of the stomach, but this is all bypassed. And here's the new stomach, which is very small, hooked onto a piece of jejunum that is brought up. Hence, we have a small stomach, and we have jejunum in contact much earlier with food. What does that do? It alters some of the hormones that see food, and I'll talk about that later. The biliopancreatic diversion is a different procedure. It's not done in certain states because it's very, very aggressive, whereby you create the sleeve like you did here, same thing, but you also bypass most of the small intestine. You bypass all of this. So what happens with these procedures? Well, first of all, you lose a lot of weight. So here's the weight loss in percent weight loss, and here are years. You lose most of your weight with many of these procedures in the first year. You lose the most weight with the biliopancreatic diversion and the gastric bypass. So you lose about 33% of your total body weight, and you basically keep a lot of that off out to 20 years. With the gastroplasty, you lose a little bit less, but you keep it off. The banding is all over the map, but you tend to keep a good part of it off, and here are the controls, patients who are on diet and exercise. We have 20-year data showing good weight loss and good weight maintenance. So why is this the only thing that we know that will keep the weight off? Here's the reason, and to simulate this, I'm just going to use the Roux-en-Y gastric bypass, because this gives good weight loss and less side effects than the biliopancreatic diversion. But you see this kind of weight loss and more with the biliopancreatic diversion. So we're creating a small pouch here. Here, this is bypassed. The rest of this stomach and this part of the duodenum is bypassed. Plus, you're hooking up a piece of jejunum to the new stomach. So what happens is you have bypassed the area of the stomach that produces ghrelin. And remember, ghrelin causes an increase in appetite. Gone. The other thing you do is the cells that produce some of the satiety hormones like PYY and GLP-1 see food much earlier. So what happens is you get full much earlier. And that is why we think that this procedure here, the Roux-en-Y gastric bypass, not only helps you lose weight through restriction here, but helps you keep it off, because you just don't, your levels of PYY and GLP-1 go up and your levels of ghrelin go down. And this is basically permanent. So your body set point alters permanently. Do you lose down to a normal body weight? No. You lose about 100 to 150 pounds. So if you weigh 400 pounds, you're still going to end up weighing 300 to 250, but your body is set permanently to a lower body set point. And this is why it's now called metabolic surgery and not just restrictive or malabsorptive surgery. So I just want to summarize. I think I've made a case for obesity being a chronic disease with a complicated etiology. Therefore, we need a chronic care model to help manage overweight and obese patients. Why is obesity a disease? It is a disease because there are complicated CNS systems that regulate appetite, energy expenditure in response to eating, and we think these systems are disrupted. We have complicated peripheral and central signals. They're integrated in the CNS to regulate body weight on a very tightly controlled system, and the hypothalamus is the primary regulation center of appetite, satiety, and energy expenditure. And remember that there are ways to alter your energy expenditure through increasing brown fat through irisin and exercise. So you've got diet, exercise, and behavioral interventions. The homeostatic control system and the reward system bidirectionally interact to affect food intake. So, you know, if you didn't have desserts available, you would just regulate your energy intake. When you're full, you're full. But we've got these enticing desserts out there and other enticing foods with high salt that trigger the reward system, and you still want to eat that food even though you're full. And that may be why, one of the reasons why it's so difficult in this highly palatable food environment to keep a certain body weight, because the reward system can override the homeostatic pathway, chiefly during periods of relative energy abundance, by increasing the desire to consume foods that are highly palatable. Think about when we were Cro-Magnon man, and we had to go out and kill a deer and get plants to feed ourselves. We were not worried about the reward system, right? We just wanted to feed ourselves to maintain our survival, to keep survival. Now we've got all of these ways of making food more palatable through technology, obviously through agriculture and technology, but we still have the genes that we had eons ago. And so when we see really good food, we want to eat it because our genes still don't know when our next meal is going to come from. We have gut hormones act peripherally to modulate digestion and absorption of nutrients, but they also act as neurotransmitters within the CNS to control food intake. Alterations in the gut hormones after weight loss are not consistent long term. So what happens is these gut hormones still work to make us regain that lost weight. And a better understanding of the role of gut hormones may offer an opportunity to develop more successful treatments for obesity. So the treatments that we have available that are drugs can help us lose about 10% of our body weight with diet and exercise. And maybe in combination we can more closely simulate the kind of weight loss we can get with gastric bypass surgery, which is about 32 to 33% weight loss, as opposed to 10%. 10% is at its best for drugs. Bariatric surgery produces long-term weight loss and alters permanently the gut hormones to maintain that weight loss. Newer anti-obesity medications may show promise. There are many in the pipeline. The goal here would be to simulate what we can do with gastric bypass surgery. So at this point, I'm ready for your questions, and I see that maybe we have some, and I'm going to start. So, first question, is the neuronal injury reversible in the animal model? That's a very, very good question. So, in the animal model, it was shown that it is reversible if you stop high-fat, high-calorie feeding within a week. But if you continue the high-fat feeding beyond 1 to 2 weeks in the animal model, it becomes permanent. Very good question. Does that prove that that's the case in humans? No, we really need to test this in humans. Great question. Next question, has iresin been tested in animals? Yes, it has. And iresin has been tested in animals and has been shown to increase brown fat development from white fat. Next question, iresin and exercise. Does the type of exercise matter, as in weightlifting versus running? That's a very, very good question. I don't think this has really been rigorously tested, but it's a very good question. It seems that that both running and weightlifting increases metabolic rate. So, but to what extent? And to what extent does iresin play in? We don't really know. Very, very good question. Next question, is there a reason why there hasn't been a drug developed to work directly on ghrelin? Very good question, and there is. There are ghrelin agonists and antagonists being researched out there very rigorously. So why would you use a ghrelin agonist? Well, to stimulate weight gain in those who are malnourished or who have a malabsorption issue and are malnourished, and you would want a ghrelin antagonist as a treatment for obesity, and that is certainly being looked at. Great question. Another question, could any of the surgical procedures be done with local anesthesia? Another good question. The answer is the ones that I have shown you, the Roux-en-Y gastric bypass, the biliopancreatic diversion, the gastric band and the sleeve are not done under local because you're really altering, you've got to get into the abdomen there laparoscopically. However, good question, some of the gastric plication that I showed you could be done endoscopically. So there is a procedure called gastric plication that is done with sutures that are placed endoscopically. So that's being researched currently. Great question. Next question, would it not be simpler to simply remove the ghrelin-producing aspect of the stomach, either surgically or pharmacologically? Yes, and that is exactly what is done with the gastric sleeve. So you remove that large piece of stomach and create a sleeve. So yes, that is currently being done, and that's called the gastric sleeve. Next question, what is your take about diets that claim to increase leptin or to address leptin resistance? Well, diets that claim to increase leptin, how do you increase leptin? How do you address leptin resistance is really the question. So you really can't do that by diet. So I really wouldn't believe a diet that claims to increase leptin? That's my answer. Leptin is produced by adipose tissue and enters the brain and causes satiety. Leptin resistance occurs probably from that hypothalamic injury that I was talking about, and the only way to reduce that leptin resistance is to stop eating bad food. So if diets that claim to increase leptin or reduce leptin resistance do so by eating very healthy food, I agree. Fruits and vegetables, lean protein, and low-fat dairy, that will address leptin resistance. Next question. If the hypothalamus has a reduced ability to detect endocrine signals for fullness after inflammation, what then about ghrelin? Would it not also become undetected and thereby prevent the ability to trigger hunger? If the hypothalamus has a reduced ability to detect endocrine signals for fullness after inflammation, what then about ghrelin? Would it not also become undetected and thereby prevent the ability to trigger hunger? Good point. I don't think we have the answer to that. So one thing I would say is that the vagus also directly sends signals via ghrelin, and maybe that is not affected by the hypothalamic inflammation, but that's a question that that is complicated. We really don't know all of the effects on these various signals by the inflammation. Excellent question. Next question, is the inflammatory effect on the hypothalamus reversible if the patient switches to a low glycemic eating habit? Very good question. This is in humans. We really don't know. My take on this is yes, that if you want to reverse the inflammation, you've got to go on a very, very healthy diet, switching to low glycemic index diets, which is just really fruits and vegetables, whole grains, lean protein, right? It's getting rid of the high sugar processed foods. And I think you can do it. I don't have proof of that, so that has yet to be researched. Kindly comment on the role of the gut microbiome in obesity, digestion of carbohydrates, and the production of appetite-related hormones and neurotransmitters. Very, very complicated, but yes, it looks as if when you do a gastric bypass, beyond all of those hormones that I talked about, what you're also doing is changing the gut microbiome towards one that is seen in a lean patient. So in lean versus obese patients, it has been shown that there is a different percentage of Bacteroides versus Firmicutes, and that is reversed with the gastric bypass. And this gut microbiota has been shown to produce varying amounts of the gut hormones that I've just talked about. In other words, that the satiety-producing hormones are increased in the lean microbiome. However, there's a lot more at play here, and it's very complicated. It has been shown that, yes, if you transplant the lean fecal matter from a lean mouse to an obese mouse, you get weight loss. Whether or not we're going to start doing this in humans is still up in the air, and it's just a lot more complicated than simply fecal transplantation. For example, what role do antibiotics play? What role do antibiotics in food play? These are all complicated issues that are being researched now. There is a researcher at NYU who feels that it could be that obese children are obese because they are the ones that have gotten more antibiotics in their young life, for example, for otitis media and the like. We have yet to study that. But very good question. And another question, should we begin to start treating the gut bacteria directly rather than treating the human patient indirectly? Well, yes, if we confirm that it is indeed the gut bacteria that is causing obesity. And we really don't know that yet. We really need more research into alterations in gut microbiome before and after gastric bypass. People are looking at that now. We need to study this more in-depthly, and the NIH is grappling with how to study the human gut microbiome as we speak. And so yes, it may be that in the future we'll begin to start treating the gut bacteria directly rather than treating human patients indirectly. Certainly, I do firmly believe that current drugs and currently available surgical options are really the tip of the iceberg. Certainly drugs are. Getting, patients to lose 5 to 10% of their body weight while giving them a drug that has side effects and having to do this permanently to suppress the appetite and giving them drugs for the rest of their life is not a good answer to me. But again, we need to study this first, and then we may be able to treat the gut bacteria directly. As you say, it's a very, very good question. These, I have to say, these are some of the best questions I've ever received after one of my talks. So I really thank you for that. And I think, unless we have any more questions, I think the broadcast is over, and I thank you so much for all of your important and very, very, these questions are questions that the researchers are asking as we speak. So thank you so much for your attention.